So good afternoon. I want to thank everybody for coming today. My name is Dr. Brett Bennington, and I'm the chair of the Department of Geology, Environment, and Sustainability at Hofstra, and a co-director for the second annual Presidential Symposium Solutions for a Sustainable Tomorrow. Sustainable solutions can be found at the intersection of science, economics, and social equity, with education playing a very important role. And there is little doubt that climate change is our largest and most daunting sustainability challenge. With this in mind, today's sessions have been focusing on climate change. As the philosopher Marshall McLuhan very presciently said decades ago, there are no passengers on Spaceship Earth. Everybody is a member of the crew. We have moved into an age where everybody's activities affect everybody else. Nowhere is this more true than in our reliance on fossil fuel energy and its disastrous side effects of climate change. So with this fact in mind, we are gathered today to address climate change from three different angles. This morning, we explored the use of project-based learning to teach about climate change so that we empower our students with an understanding of its causes and effects. Now we are gathered for our keynote speaker, Dr. Amy Marschilok of Stony Brook University and Brookhaven National Laboratory, who's going to talk about some of the technical aspects of how we transition to an energy grid which is based on carbon-free energy. And just want to mention that Dr. Marschilok will be signing her book if anybody wishes to purchase a copy after her talk at the table out in the front there. And then immediately following this, the keynote session at 2:40 p.m., if you can stick around, because we are going to have a panel discussion on the greatest climate disaster to impact the New York region yet, Superstorm Sandy. And we are fortunate to have Dr. Adam Sobel of Columbia University joining us, who's the author of a book called Storm Surge about extreme weather and climate change. And my wife texted me a few minutes ago and reminded me that this is the anniversary of the 1938 hurricane that devastated eastern Long Island and New England, and also the anniversary of Hurricane Hugo, which impacted Long Island. So storms are the order of the day. Anyway, so with that, let me introduce with great pleasure the president of Hofstra University, Dr. Susan Poser, who will introduce Dr. Marschilok. Thank you.
Well, good afternoon. We got this one at 1 o'clock on what I think is going to be the last day of summer, truly. But it is being recorded, and I know will be watched widely on our campus. So thank you, Brett, and I also want to thank you and your co-chair, Martine Hackett, and of course, Athleen Collins, for doing a wonderful job putting this symposium together and involving our entire campus in a conversation about sustainability and what we can do as a community and as a campus. I've attended several sessions so far. They have all been so interesting and so different from each other. So I really commend all of the organizers of this. So it's my pleasure to welcome everybody to the keynote address for Hofstra's second annual Presidential Symposium. This symposium occurred for the first time last year and was so successful that we decided to make it an annual event and to incorporate it into the month-long September welcome that begins the new academic year at Hofstra. It is important, it's an opportunity for each school and the College of Liberal Arts and Sciences to come together to discuss an important topic of local, national, and global interest and to engage in service activity around that topic. This year's symposium, Sustainability Solutions for a Sustainable Tomorrow, puts a special focus on Hofstra's role in making our own campus and our community more sustainable. We are showcasing and sharing information about the research, scholarship, curriculum, and service that's going on at Hofstra, and inviting researchers, scholars, and community members to share their expertise and best practices so that we might learn from others about the kind of research and practices that will make our campus and our community more sustainable in the future. Today's keynote speaker is a scientist who works on renewable energy technologies and the critical role of energy storage in making these technologies more reliable, both for the power grid and for individual use. Dr. Amy Marschilok is currently an associate professor in the chemistry department at Stony Brook University, where she holds a joint appointment as a manager and scientist in the Energy Storage Division Interdisciplinary Science Department at Brookhaven National Laboratory. Dr. Marschilok, who received her BA and her PhD in chemistry from the University of Buffalo, has a primary research focus on the chemistry of batteries, high-density energy storage, and emerging battery technologies. She has published over 188 peer-reviewed scientific papers to date and is responsible for over $39 million in grant-funded research. With her colleagues, Dr. Esther Takeuchi and Dr. Kenneth Takeuchi at Stony Brook University, Dr. Marschilok founded the Institute for Energy Sustainability and Equity, whose mission is focused on electrochemistry and energy storage to address energy-related environmental issues, and human health. Advances in the basic science of energy storage are critical to enabling the expanded adoption of renewable forms of energy and a clean, green, resilient electric grid, as well as enabling the widespread utilization of electric vehicles. Dr. Marschilok works to educate energy leaders and prepare students and early and mid-career scientists to become the energy leaders of the future. She's also leveraging the Brookhaven National Laboratory to mobilize and engage private and public partners in impactful new programs related to energy and the environment. Dr. Marschilok, we're delighted to have you here. Please join me in welcoming Dr. Amy Marschilok.
Thanks very much for the gracious introduction. It's really a pleasure to be here on Hofstra's campus and to have the opportunity to talk about these themes. So I'm really delighted to describe some of the work that we're doing at Brookhaven National Lab and at Stony Brook University towards the goals of advancing our sustainable energy future. And what I hope to highlight is some of the work happening at Brookhaven Lab within the Energy Systems Division. And next, I'll translate to some of the work that's happening in the Energy Storage Division at Brookhaven and at Stony Brook University. And the theme I really hope to highlight is that by thinking about energy in a holistic way, encompassing energy storage to energy systems, we can really gain insight and advance towards a more sustainable energy future. And so the National Academies has recognized decarbonizing the energy system as a really critical goal for the US. This report issued just this past year on accelerating decarbonization of the US energy system. And if you hadn't had the opportunity, I'd encourage you to look. There's many important recommendations made in the report and a very holistic view of the current state of our US energy system. But I'll note that the National Academies has highlighted that to achieve a goal of net zero by 2025, we really need an interdisciplinary approach, thinking about electricity generation and use in multiple ways. So advancing toward electrification was identified as a real opportunity area, and this includes electrification in transportation, in buildings, and in industry. Also improving energy efficiency and productivity of energy generating systems, and the production of carbon-free electricity. Finally, expanding the innovation toolkit in multiple areas was recognized as critical to decarbonizing the energy system. So the National Academies called out that there are promising technologies that we could advance, but there's also additional work needed in this space from basic research through and on to applied research. And so it's been exciting to see energy justice and energy equity as emerging themes, both in the US and abroad. When we think about energy justice, there's multiple ways we can think about it. One is distribution of resources. So how are resources allocated? Where are they distributed? Next is procedurable. Are there equitable procedures to engage stakeholders in a non-discriminatory way? And this really crosses over into social consciousness and ways that both social scientists and scientists doing hard physics, hard chemistry, hard materials can impact. And there's also a need for acknowledgement and fair representation in terms of recognition. And so I think this clean energy is a space where many of us can have impact despite our discipline, and there's real opportunity to work together to advance these goals. And so if we look at this table and think about some important contributions toward energy justice, availability, having sufficient energy resource of high quality is really essential. And that's a theme I'll return to. What does high quality mean? How do we get a high quality energy resource? Also having sustainability, so energy resources that can last into the future and be available to us both as a community and as a nation. And then finally, taking accountability for protecting the natural environment, minimizing environmental footprint. There's real opportunity for all of us in these regards. And so if we look at US energy consumption and how it's described today, I'll start with a view of 2017, and then I'll go to a more modern view. This is a very helpful report issued by the Energy Information Association, and in 2017, it was actually credited to Lawrence Livermore National Lab. So what we're looking at here is energy generation on the left, energy use on the right, and the size of the bar represents the amount of that resource going to that use case. And so a couple important things to note. In 2017, we can look at the overall US consumption of energy, and a large contribution to that is to energy generation. But what's been really interesting to me over time is the amount of energy that we lose and are unable to access over time related to our electric grid. The grid as of 2017 was noted to lose about 67% of the energy it generates, and furthermore, 79% of the consumed energy still originated from natural gas, coal, and petroleum resources. So you can see our renewable sources, solar, nuclear, hydro, wind, and geothermal here, but they were making up a very small overall contribution to energy generation and energy services at that time. And so if we think about US energy consumption now in 2021, the situation has improved a little. So we're up now to 12% renewable energy resource, and an additional 8% here broken out for nuclear energy, which could also be considered green. You can see a contribution from biomass, from wind as a resource at 27%, solar at 12%, and hydroelectric at 19%. And here in New York State, we have hydroelectric resource, we have opportunity for solar, for geothermal in some locations, and also for wind, especially for offshore wind here on Long Island. So it's an exciting time to see renewable energy and the great opportunity we have for further decarbonization in this space. So if we look at our energy consumption, there's still a significant electrical energy system loss. And so, one of the challenges with the way our electric grid works today is that the energy we produce needs to be used when we produce it. There's not sufficient resource to store that energy and to access it on demand. And that also causes issues when we think about integration of renewables. There's a great energy resource available there, but if that resource is intermittent, we need ways to make that energy a high quality energy and an energy that can be accessible to multiple people. And so it's a complicated equation when we think about energy generation, we think about energy use. I'd say New York State is really an exciting place to work because it's really shown leadership in thinking both about technology and about community needs and the needs of multiple stakeholders. So the Climate Leadership and Community Protection Act, issued in New York State, is requiring now state agencies, authorities, and entities to direct funding in a manner designed to achieve goals for disadvantaged communities with an objective of disadvantaged communities receiving 40% of overall benefits of clean energy spending, and seeing alignment of New York goals and federal goals in this way has been very exciting. New York has also established climate justice working groups that are thinking about specific criteria, and so reducing pollutants, addressing greenhouse gas emissions reductions, and also thinking about the regulatory space in this area. And so one example of this is thinking about generation related to fossil fuels and to coal. There is a history of peaker plants here in New York State and here on Long Island, which are used to produce electricity in times of very high demand. The hottest days in the summer, the coldest days in the winter, when we have a need for electricity that exceeds the normal use of the electric grid. Notably, more than 1/3 of New York's peaker plants burn oil, and 3/4 are over 30 years old. Some of these plants are in very dense urban areas, and these contribute 97% of nitrous oxide emission in New York State, according to this report by PSC. And so these are some of the things that motivate me as a researcher and motivate the scientists in my group. Thinking about the opportunities we could have for further integration of renewables, the opportunities we could have through additional integration of storage to move towards a cleaner, greener, more resilient grid. And so, as I said, I'd like to start by highlighting some of the work we're doing at Brookhaven Lab in the energy systems space. So we have a group focused on energy efficiency, and we're doing this from the household level to the systems level. Particularly in dense urban environments, we can have significant improvements in rethinking the way that building efficiency works. As we go to more isolated regions of New York State, even redesigning the way our fuel systems work and the way we use heat pumps can be very impactful. And I'll give an example of that. The group's also looking at alternative fuels, including biofuels. Hydrogen we see as an emerging opportunity, and there's real interest in that, both nationally and in New York State. And so the group is thinking holistically, both about the efficiency of the system and about the emissions-related outputs. So measurement, analysis of emissions is a part of their work. We also have expertise in geothermal materials and systems that I'll discuss briefly today. We have a group on grid modernization and grid modeling that is working to project and predict how the electric grid would work under different scenarios, including with increased penetration of renewables into the electric grid and increased deployment of storage. So we're using data analytics, we're using machine learning. This is a large capability at Brookhaven Lab, being able to predict or project how these systems might work can then reduce risk for utilities and developers. We're also thinking about risk in different ways and ways to control and assess what's happening in these dynamic processes. And then on the energy storage side, we're doing studies to investigate how batteries function under operation, looking at batteries both for electric vehicle and large-scale grid applications. And I'll discuss these examples in more detail as we proceed in the talk. And so starting in the energy efficiency space, an exciting example of work in the group is looking at heat pumps, which can be used in cold climates and having improved efficiency and reduced emissions for wood stove heaters. And so Tom Butcher in our group is a real expert in multiple types of fuels. His team leads a wood heater design challenge annually where they look at different designs and opportunity to reduce emissions from multiple sites. They're also doing measurements to support development of air pollutant emissions factors. So being able to quantify outputs from the system is another interest of the group. And then thinking about solid oxide fuel cells, opportunity to use both gas systems and gas hydrogen blends has been an area of interest for their group. Tatiana Piantina in our energy systems group is looking at geothermal materials. So the concept of geothermal is to have very deep, geologically based energy storage systems where we can actually take advantage of differences in temperature deeper in the earth and on the surface of the earth as a way to store energy and gain energy efficiency. So one of the challenges for these systems is the materials that we use when we dig that deep well. They're exposed to a variety of temperatures. We want them to be resilient over time with limited degradation, limited corrosion. And so Tatiana and her group are looking at new materials, new types of cements, and actually collaborating with partners internationally in thinking about these challenges. So understanding how does the material wet? Can they control the interaction with water to make it hydrophilic or hydrophobic? And then responses to cracks, ability to self-heal and reduce degradation over time have been areas of interest. And so in the energy systems group, we also have talented scientists, Meng Yue and his group, looking at developing a greener, more resilient electric grid. The grid is such a big topic, I wanted to give some introduction and context before discussing the specific work there. And so if we think back over the history of our electric grid, New York's played a very important part in that history. So the Pearl Street Station in New York City was one of the first examples of our first advance toward an electric grid. So this was a coal-fired energy generating plant. And at the time, when this idea first developed in the late 1800s, these generating plants were isolated and were really serving dedicated customers. So over the next 5 years, there was an advance. Within 2 years, according to the Edison Technology Center, the Pearl Street Station was then serving 500 customers. So it's this idea of a local grid that can provide energy to a community. And over the next 50 years, the utilities then began thinking about linking these multiple generating plants into these isolated systems. And in the mid-1930s, additional connections were created to bring additional reliability to the system. So the intent was to have a system which could have access to backup generation in times of equipment failure, unexpected demand, or routine maintenance, and to also improve the economics of the system through reserve sharing and through access to diverse energy resources. And so by the mid-1960s, as noted by the U.S. Department of Energy's Office of Electricity, we had moved toward an electric system that was an interregional electric grid. And now our grid is a very complex network of systems that really involves engagement across multiple utilities, multiple sectors, and multiple states and regions. And so the U.S. National Academy of Engineering recognized electrification of our energy system as one of the top 5 engineering achievements of the century. And so, celebrating a century of innovation, it was highlighted in that regard and held up along with the automobile, the airplane, water supply and distribution, and electronics as really a great engineering achievement. And so I think today, as we look back at that advance and as we think about the grid of the future, there's some existing challenges we can consider, and there's also some emerging challenges we can recognize in thinking about our future electric grid. And so, first is congestion in certain areas. In areas where we have high people, high power density, we can have power bottlenecks and a disconnect between the age of the energy providing system and the population and the energy demand for that system. And so we can see this both in the US domestically and internationally as well. And it's especially prevalent for us here in the New York region. Peaking is another challenge to think about. So this is the idea of thinking about energy demand and energy supply. So at different times of day, we all want to use energy at the same time. At night, it may be cooler. In the summer, it may be warmer, depending on the day in the winter. But the energy demand and the energy supply don't always line up. So matching the investments is an important challenge. Thinking about reliability and power quality is important, and this has a very direct economic impact. So you can look at specific reports describing the overall impact of power loss to a consumer. So this can be a situation that's important at the household level, but also very important economically to a company or to a region. And so even a momentary interruption can have a very significant impact with much more impact from a sustained interruption in these spaces. And so this is one example from the Wall Street Journal, a specific threat to Toshiba, where an outage of 0.07 seconds resulted in 20% chip reduction for 12 months. So depending on the specific technology you're working on, having resiliency and reliability is really critical. Having recovery and timely response in the case of extreme weather events is also essential. Being able to have real-time knowledge of how that energy is distributed, being able to recognize when we have outages, and then respond to those outages is a real need. And so it's been noted recently that as our extreme weather events are rising, there's an even greater need for a focus on US grid resilience. And we've seen that in many recent news reports, both here and in other parts of the US. And so if we think about our emerging grid challenges and opportunities, it's really integrating new renewables. We need more knowledge and planning about where to locate them. We need to understand their variability over time. So what's the variability of a solar or a wind resource? How do we understand that and predict it? And then being able to address needs for effective transmission and effective storage so that then we can smooth out these variations and provide reliable energy over time. Vehicle electrification is another real opportunity. It's been recognized as a real opportunity to decarbonize and move toward a greener electric grid. But as we increase the amount of EVs, the way we charge them, where we charge them, and how we charge them can create demand on the electric grid as well. So there's a lot of existing and emerging challenges to balance. There's opportunities in thinking about the size of our electric grid and the distribution of our electric grid as well, both in the US and internationally. So these are some images back from Superstorm Mariah. And we note here that when Mariah hit Puerto Rico, you can see the difference before and after in terms of the amount of devastation this loss in energy provided to the community. And so I talk to students about this a lot. If they're passionate about helping people, if they're passionate about affecting quality of life, access to clean, reliable energy directly scales with metrics for quality of human life. And when you have situations where you're without power, if your hospital's without power, if your company's without power, if your home's without power, it's one of the biggest impacts that you can have on a person. And so I'm really excited to be working in this area, not just because I find the chemistry and the material science interesting, but because I see a real opportunity to impact energy equity, to impact energy justice, for a broad community with these ideas. And so a little about the current capabilities in grid modeling and the efforts we have to advance grid modeling at Brookhaven National Lab. So we're using simulation capabilities. So with effective data, we can do a lot of this work using a computer and using mathematical-based models. So understanding both the steady state and the dynamic properties of a renewable resource, we can then introduce that renewable and see the impact it has on the function of the grid. And by using machine learning and using the large data analytical resources at the lab, we can then begin to identify anomalies, detect them, and then begin to predict behavior under different conditions. And so by having predictions that can function over different timescales, the vision is to then be able to reduce risk to grid developers. So being able to quantify and model uncertainty, being able to predict sizing and storage and siting of storage resource sources, and then also thinking about forecasting and how climate forecasting can play a role. And so I'll show one slide here highlighting the idea of integrating forecasting capability with grid modeling. So this was a collaboration of Meng Yue in our Interdisciplinary Science Department and Mike Jensen in the Environmental and Climate Sciences Group at Brookhaven National Lab. And so what we're looking at here is reflectivity data. So this is weather data which reflects precipitation and wind by the color of the reflectivity as shown here. And so if you look at the reflectivity, you can actually use this as a way to predict storm-related utility outages. So we're thinking specifically of outages here that relate to overhead power, because loss of power lines in many areas of New York is one of the biggest sources of loss of power and time difference for power to come back online. And so this model was calculated for 5 areas of the utility service territory. We used both hourly weather condition data and data from the utilities component, so looking at data from Orange and Rockland Utility, and then using this Bayesian update approach, considering both failure rates and known outages, so linking the weather data to the outage, we can then begin to predict conditions and predict the impact these outages can have. And so we look forward to continuing to work with utilities in these regards to help them assess and predict impacts of extreme weather events. And so I gave the federal perspective from the National Academy's Deep Decarbonization Report. I also wanted to comment on some of the specific energy goals identified by New York State, because I think New York really is an energy leader in this space and really is a region that's advancing clean energy in such important ways. So these are some notes from Governor Hochul's most recent State of the State address in 2022. She set goals for 2025, 2027, and 2030 that are all very exciting and very aggressive. So you note goals around clean energy, goals around integration of renewables, goals around green energy jobs, and goals around retirement of fossil fuel facilities, as I mentioned earlier. What I wanted to talk about next is why energy storage shows up so much in these goals and the opportunities we see for specific approaches to new energy storage technology and characterization of the function of energy storage systems, and why we think this work is so relevant and so important to address New York and the nation's energy goals. Because at first glance, we all use batteries every day You know, they're pretty ubiquitous in our everyday lives, but from afar, they seem pretty similar. It's not obvious why multiple technologies would be needed. It's also, you know, not obvious why we've set such, you know, specific numbers here and how they link to green energy and clean energy. And so I start with a slide from my colleague Esther Takeuchi, as presented at the Ashton Carey lecture. The goal here was really to link the application which uses the battery to the requirements of the battery system. And so it's really important to recognize that for the battery that we use in our cell phone or laptop, there's a different set of requirements, a different set of demands than the battery to power our electric vehicle or the battery that we would use to power our electric grid. So each battery has unique materials, unique engineering approaches, and unique design of construction. And if we think about these in a deliberate way, we can have opportunities to specifically address some of these goals. But it's useful to recognize the different demands of different use cases and to show, you know, what's important in each situation. So in the case of our, you know, consumer electronic, you know, cost is very important. It's important in our EV, and it's important in grid level storage as well. But the trade-off between how long we want the battery to last, for example, is very different. You know, I'm happy to get a new cell phone every few years, but I don't want to replace my electric vehicle or replace that battery on the grid with the same frequency. The safety demands for the systems are very different. We have a small battery here. We have a bigger and a bigger battery there. And so I hope to highlight some of these examples and give you some thoughts about green energy opportunities in battery research within these next and following slides. And so if we think about consumer electronics, the key here is really to have a system that's lightweight, that's low cost, that's a high energy system. And the lithium-ion battery technology, subject of the recent Nobel Prize in chemistry, was really foundational to enabling our consumer electronics. So this lithium-ion technology allows us to have, you know, lightweight portable cell phones and laptops. It was pioneered by John Goodenough, Stan Whittingham, and Akira Yoshino, and really important advances made by Sony on advancing the battery technology. And so the way this battery works, we have a lithium-ion that shuttles back and forth between our two electrodes. We have an electrode based on a specific carbon type, so they're showing a petroleum coke here. And then we have metal oxide, so cobalt oxide here at our positive electrode. And so what's great is that lithium-ion is very lightweight, it's very small, it's high voltage, which gives us high power for our battery system. And so it really meets the needs and demands of our portable electronic devices. As we think, however, about electric vehicle batteries, there's some additional parameters to consider. While we still want a low-cost system with high energy density, opportunity for improved duration, improved lifetime takes on added significance for these systems. There's also a desire here to use more sustainable materials. So cobalt is sourced from very specific regions geographically. It's expensive. It's not an environmentally friendly material. It's not friendly to human health. And if we think about security of material supply, the typical lithium-ion technology has some issues relating to raw materials and raw material resources. And so if we think about going, you know, toward electric vehicles, it's something we definitely want to do to get greener. Thinking about the specific chemistry, the specific materials in these EV batteries is really an opportunity. And so first, a look at how far we've come. So this is a slide showing our electric vehicle charging infrastructure. So In 2008, looking at this report from the National Renewable Energy Lab, we had 430 EV charging outlets in the US. As of 2018, there were over 50,000 EV charging outlets. And you can see here with this latest data at 2019, we've advanced today far beyond, 100,000 count. And for those thinking about making the jump to an electric vehicle, I think it's really an exciting time to go toward a plug-in based electric vehicle. One of my colleagues has just done this. And so if we look now at our electric vehicle stations and where they're located, you can actually find very helpful information on NYSERDA's website, the New York State Energy Research and Development Authority. It describes where the charging stations are located. You can do maps and zoom in for different regions. And you can even type in a starting point and a destination. So for fun, I looked at the travel from Stony Brook to Hofstra's campus. You can see the multiple charging stations available to do this. And if you wanted to go to the Grand Canyon from Stony Brook, there's actually a continuous path of electric vehicles there as well, charging stations as well. So, what are the things we're thinking about for electric vehicles? We've got increased emphasis on having an electric vehicle charging network. California has already made the recommendation and the jump that they're going to go all electric, in the near term for as a state. But one of the issues which has limited consumer adoption of electric vehicles is thinking about that time, relating to charging of the system. And so we can have the opportunity to charge today's EVs directly using our home-based electric grid, which is great. So if you buy a plug-in hybrid, you can charge it today off your regular 120-volt outlet. And as noted by Forbes, you get a charging speed of 3 to 5 miles worth of charge per hour of charging if you use your regular 120-volt outlet. You can also install a level 2 charging system at 208 or 240 volt. This will allow you to charge 12 to 80 miles per hour. And then for certain electric vehicles and for specific charging stations, there's opportunity for charging speeds of 3 to 20 miles per minute with these specific DC fast charging stations. So the technology's come really far. There's a lot we can do with EVs. I really think they are a exciting and practical technology for us all to use today. So this is an image from Toyota that describes the different charging systems. But an opportunity defined by the US Department of Energy was to think more about fundamentally what's limiting that charge time in a battery. Can we make batteries charge even faster? And can we redesign the battery a little bit to make that a possible solution? And so it still takes much longer to charge our EV in our wall than it does to charge to fill up our gas tank. And so the goal that Department of Energy set was a 10-minute charge time for electric vehicle batteries. And so what's the challenge in doing this? When we charge our battery, we want our lithium-ion to go back to its home location. And it's really critical that the lithium goes back in an organized way, where we have reinsertion into the host framework, and we maintain a smooth, flat structure within our battery. Under certain conditions, particularly under fast charge times, you can have situations where that lithium deposits in a non-uniform way, and in some cases, you can have formation of dendrites, which can penetrate the battery separator and then cause an internal short circuit between your positive and negative electrode. And so for batteries which are well characterized and well understood, the developers limit the charging properties of the battery. So the electric vehicles on the market are designed in a safe way so that you cannot charge it too fast. You cannot create an unsafe charging situation for your battery. But at a fundamental science level, if we can actually redesign this interface and change the way that lithium deposits in our battery system, we have opportunity for new technology which can charge safe and fast and very effectively. And so the idea here, and this was really a collaboration of Stony Brook University and Brookhaven National Lab, my colleague Esther Takeuchi, David Bach at Brookhaven, and Ken Takeuchi were important contributors here. The idea was to affect the overpotential for lithium deposition by introducing a very thin coating on the surface of the battery electrode. And this was work that we did at a pilot scale at the Center for Functional Nanomaterials at Brookhaven National Lab. So the CFN has an outstanding characterization suite of tools looking at materials, looking at interfaces, looking at properties of different systems. You can actually write proposals to access CFN and to do work there with scientists in that space. It includes a very high quality clean room, high quality microscopy facilities, and other characterization tools. And so here's how the system works. We're starting with a carbon-based electrode again. We want our lithium to go into our carbon, and by introducing this very thin coating, we're actually changing the propensity to form those dendrites. So what we're affecting, in a way, is the thermodynamics for that deposition process. And so it was important to verify that we could make very thin conformal films. We're using nickel in this case. We can make these using a well-defined sputtering process. So this is a 10 micron. So microns are the order of a human hair. So we're looking at a very, very thin coating here. It adds no significant weight to the battery. We can make it using very simple processing approaches. And we've now have intellectual property on the concept and multiple publications that show the benefit of the system. And so we've been able to verify that there is a reduction in limiting plating, lithium plating under very high current charge conditions. That also translates to an increase in efficiency over extended cycling of the system. And so this is an area where the US Department of Energy invested in the fundamental science. They also invested in the opportunity to scale and grow the technology. So in collaboration with the New York State Energy Research Development Authority and the Office of Technology Transitions from DOE, we were able to collect data on batteries of larger and larger size and to show the scalability of that technology. So for this project, we really wanted a system that was consistent with existing manufacturing process. So that's been a fun project and a fun area of interest for Stony Brook and Brookhaven. Another issue, an area of opportunity for these systems is thinking about how they function over time and how they function over different use cases. And so if we charge a battery fast, that makes a difference. If we operate a battery under different temperatures, that makes a difference. If we pause the charging, or if we pause the use of the battery, that can also make a difference in some cases. So another great resource at Brookhaven National Lab is the National Synchrotron Light Source 2. So this is a very bright light source. So a synchrotron is a ring where we have electrons, a very large source of electrons going around this ring. To give you a sense of scale, these are cars here. We could fit a baseball stadium in the center here. So this is a $1 billion investment by the US Department of Energy and multiple investments for specific experiments following that first investment. This is also a user facility that's accessible to the broad community through a proposal process where you can write proposals, collaborate, and do work with scientists. And so in this case, what we were looking at was lithium, nickel, manganese, cobalt oxide. So you can see we've still got cobalt in the system, but we're reducing the overall cobalt from lithium cobalt oxide by incorporating manganese and nickel in the system as well. So this is a material that's of interest for large-scale batteries, including vehicle technology batteries. So we've been looking at differences in electrochemistry, differences in surface condition, and also quantifying and tracking structural changes under different conditions. An important part of that equation is quantifying the work or the useful energy of the battery versus the heat output of the battery. If we think about a laptop or a cell phone, heat is a nuisance. It's a sign of inefficiency. But if we have a vehicle battery getting hot, if we have a grid scale battery getting hot, if it's not a controlled situation, there can be significant safety issues. And so we're understanding the conditions under which heat is generated. This will also contribute to lower cost energy storage systems in the future. If you purchase a Tesla today, your Tesla doesn't have a single big battery. It has, hundreds, sometimes thousands of very small laptop-sized batteries, which are all surrounded and supported by a cooling system to manage that thermal energy. So looking at different materials, different use cases, and understanding that heat work trade-off is something that we're also very invested in. And so here's an example of the type of measurement you can do at NSLS2. So we can actually measure a battery inside a stainless steel can. We can do X-ray measurements right through stainless steel, which is very challenging to do. You need a very bright light source like a synchrotron. And here we were looking at an Fe3O4-based electrode. So we're using an iron-based material for energy storage. Fe3O4 is a type of rust. It's very environmentally friendly. And we can use NSLS2 to evaluate how much of that magnetite, Fe3O4, are we accessing during this use of the battery. So you see this bright area here corresponds to the usable part, and then we've got this additional part here, which is not accessed and is not used in this experiment. And so then my colleague, Ken Takeuchi, who's a real expert in inorganic materials and structure-property relationships, did a deliberate redesign of this material to make that size smaller, to make the ion transport faster. And then in collaboration with Alan West and his group at Columbia, we were able to get understanding of the impact of size and aggregation or deaggregation on diffusion processes. And I wanted to highlight here that one of the important co-authors on this paper was Christina Kama. Christina actually got her undergraduate degree here at Hofstra with Professor Sobel in the Department of Chemistry. She was an outstanding student, got her PhD with us. She finished her PhD in 2017, and her goal when she started had been to go directly into academics after finishing her PhD. So in 2017, she went to St. Cloud State University as an assistant professor. She just let us know that she's received tenure and promotion to associate professor this summer. So we're very excited about that. And so what this model helped us to develop was the new approaches to think about the distribution of the material within the electrode and the impact that a three-dimensional porous electrode structure could have on function. And so you can see now, by redesigning the material in the system, we can get full utilization. We can realize this utilization under faster and faster rates, faster and faster use. And so using the synchrotron light source in collaboration with the expertise in chemistry and materials science, by looking at these batteries under operation and using this special tool, we're closer to having green materials for our future batteries. And so in terms of lithium-ion, we're thinking about systems that use different mechanisms for storage, including conversion and alloying, with silicon as an example. We're looking at fast charge, as I mentioned. We're looking at earth-abundant materials like iron, and we're also working to understand failure modes and lifetime of the system. And this failure mode understanding and quantification has been of interest both to the Department of Energy, also to Mercedes-Benz Research and Development North America, and we have a project with Army Research Lab looking at function of batteries under extreme environments because the use case of the battery is really important to how it functions. Another important initiative at Stony Brook University has been our Energy Frontier Research Center. So this is a multi-institutional, multi-year center funded by the U.S. Department of Energy's Office of Science. So Stony Brook is the lead institution. My colleague Esther Takeuchi is the director. I serve as deputy director, and my colleague Ken Takeuchi is the strategist for our center. And so our mission has been to think about these battery systems over multiple length scales, from the atomic level to the full functioning working system. So we started as a center in 2014. Every 4 years, we've written a proposal for a competitive recompetition to continue our center's work. And we were very pleased this year to have our second successful renewal and recompetition of the center. And so we started thinking about multiple length scales. We're thinking now about scalable energy storage, so how to get bigger, safe batteries with high power, high energy, and long life. And we're also keeping an eye on this theme of minimizing heat, maximizing useful work for energy storage. So M2M was our first name. M2M over T is thinking about molecular to mesoscale over time. And now we're modernizing with a hashtag S. So S stands for entropy, and we're thinking about harnessing entropy in these future battery systems. So if we think about grid scale storage, and we think about that overall challenge of scalability, there is an increased need for sustainable materials. There's a real need for security of supply, because we want to deploy these big batteries. We want to be able to deploy them consistently over time. We need batteries that are safe, so we can put them next to our hospitals, next to our schools, in our dense urban environment. And we want to have a very reliable long-term performance. And the Department of Energy has recognized this as a goal. There's a very exciting cross-department initiative at the U.S. Department of Energy called the Energy Storage Grand Challenge. There will actually be a meeting next week, and also opportunity to attend virtually. So if you're interested, I encourage you to look up Energy Storage Grand Challenge and to register for the virtual meeting. The goal is really to continue to develop U.S. innovation with the goal of innovating here, making here, and deploying everywhere. And for long duration storage, long lifetime, scalability, safety, and efficiency have been recognized as opportunity areas. And so we want to deploy energy at large scale to provide resource adequacy to the grid and support decarbonization of the system. We want energy storage solutions that can last for multiple hours in the case of an outage. And the community is still thinking about the definition of long duration. How long is long? Are we talking 10 hours? Are we talking 8 hours? Are we talking beyond diurnal? But the overall goal, again, is to meet the needs for long duration and also to harness storage to reduce these differences in peak demand. And so I collaborated with Dr. Lei Wang at Brookhaven National Lab. We also had a postdoctoral associate, Garrett Wheeler, on this report. And we did an analysis of what's happening in the energy storage space in terms of deployment for energy storage on the grid. And I was really flattered that Hofstra and the bookstore brought some of the books here. That's really exciting. So I'll be happy to talk to you and sign if you wanted to have a copy of this book. So here are some of the main findings. If we look here at deployment of grid-scale energy storage systems, you see from this gray data here that the deployments are still largely lithium-ion based systems. We've got almost 70% of the gray as lithium-ion technology. And I told you some of the challenges with lithium-ion for big battery deployment, right? We've got issues with safety, we've got some issues with sustainability of materials, but it's still a great low-cost solution. It's been really advanced through U.S. investment in vehicle technology, and so it will continue to be deployed and distributed over time. An area where we see a very interesting opportunity is from the perspective of these zinc-based battery systems. And this pink is just a tiny sliver, but we think it's really promising, and I'll show you why in just a minute. Other operational beyond lithium-ion systems that are under investigation are lead acid, so taking that technology that's used in your car today for starting up a conventional gas-based car. Also looking at flow-based systems, and then looking at systems which can be based on sodium as an alternative to lithium-ion. And so some comments on looking towards scalable energy storage and some of the work we've done at Stony Brook University and Brookhaven. We've looked at this idea of thick but porous electrodes that can give us high energy density quickly, and then been thinking very carefully about transition metal systems which can translate from non-aqueous to aqueous use. And vanadium oxide is one example, and we've seen real promising extended cycling both in non-aqueous and aqueous-based systems. So we will continue to investigate the lithium system, and we will continue to investigate the alternative, zinc-based system involving vanadium oxide. However, if we transition now to zinc, we think this is a real opportunity. So building on the type of alkaline chemistry that makes your conventional alkaline battery work, but then looking at alternative materials, molybdenum, manganese, and here harnessing materials like molybdenum and manganese as catalysts, but then incorporating oxygen from the air as an active material, we see real interesting opportunities in this space. And so being able to characterize the systems is really valuable. When you're working with water, it has different ranges of stability. You want to avoid gas evolution in the system by controlling the range so that you don't generate either hydrogen or oxygen as gaseous products. And so as chemists, we look at these questions, and this was an interesting optical electrochemistry measurement we did. So you can see the gas evolution here in the case of this conventional concentration zinc electrolyte. Here, if we change our electrolyte to a more concentrated system, we get a much more stable behavior without that gas evolution, and that translates to real improvement over extended cycling. So we see addressing this lifetime, this extended cycle life as an opportunity, and that's where we're going to continue to focus moving forward. So these measurements were done by Lei Wang at Brookhaven Lab. We've also been looking at chemistries based on manganese. Manganese is great as a very sustainable material. One of the inherent chemistry challenges for the chemists in the audience is that Jahn-Teller distortion that the material undergoes. My colleague Ken Takeuchi has developed some interesting approaches, including crystallite size control, targeted transition metal substitution to have nice retention and preservation of the host structure under different conditions. And what's great about this manganese system, these batteries can function both in a lithium host and in a zinc host environment. And so as we go to an aqueous zinc-based system, one of the real differences we see is the amount of material that starts at our solid and then enters the liquid. Every battery has, almost every battery has a liquid inside, which serves as the pathway for the lithium ion, the zinc ion, to go from the positive to the negative side. And typically, you think of that liquid as the transport for just the lithium or the zinc. In the case of our manganese-based battery, using zinc as our host, we actually see very interesting changes over time where we can actually see parts of our manganese electrode dissolve and go into our electrolyte, and then, very importantly, redistribute and redeposit on subsequent cycling. And so this has been a real area of interest and investigation to the community. How are we storing zinc? What's the mechanism for zinc storage? we see real opportunity here with manganese as a host, both for insertion and for these interesting conversion chemistries. So involving different types of scientists in the project has been exciting. There's engineers to think about porosity. There's also chemists, electrochemists, thinking about the material, and really fundamental questions like solubility are really important. And so what we've learned about this system using the power of that synchrotron light source at NSLS2 is that we can have a reversible, repeatable dissolution and deposition process. Having manganese enter solution is not bad in the case of the zinc battery. And so, this entropy theme is something that we will investigate moving forward. So to wrap up and summarize the battery half of the talk, we really see that investigating these systems using multiple length scales has been valuable. Thinking about the structure of the material, thinking about the distribution of the material within the electrode, and thinking about the full working system are all very important. We want to characterize how the system changes over time. We want to link that to the use case, whether we're doing fast charge, whether we're doing long duration storage. We want to understand how the system behaves under those conditions. And we need to quantify and characterize heat, associated side reactions, and gain a grasp and understanding of them as well. And so some acknowledgement slides. This is a slide showing our energy systems and energy storage group at Brookhaven Lab. So these first two groups are the scientists within the Interdisciplinary Science Department, and I'm really fortunate to collaborate with and manage these very talented group. Also wanted to highlight Esther Takeuchi, who serves as our department chair in the Interdisciplinary Science Department. In the Environmental and Climate Science Department, Allison McComiskey is the department chair. Mike Jensen and Satoshi Endo contributed to those climate modeling studies I described. So they did the meteorology and atmospheric modeling, and then worked toward developing the model in collaboration with Meng Yue, who's our grid modeling expert in the department. Also wanted to collaborate and acknowledge the great work with acknowledge the great collaboration through the Center for Mesoscale Transport Properties. As I said, we have multiple participating institutions across New York State and across the US, and it's really been a fun and effective collaboration with these great scientists. And finally, an acknowledgement and thanks to our research group and our affiliates for the Institute for Electrochemically Stored Energy. It's been a real privilege to work with each of them. Ken Takeuchi is a distinguished teaching professor at Stony Brook, joint appointment at Brookhaven Lab, and has really been the materials innovation lead, driving a lot of these science studies. Really a great group of graduate students and postdocs contributing to the project, and I showed their acknowledgements on the individual slides. So thank you so much for your attention. I'd be delighted to take questions.
We need to use the microphones in the alleyways for questions. So if you have a question, just come up to the microphone. Either one.
Thank you. That was very interesting. I'm curious about the manganese being better than cobalt. What's the if you could speak to that a little bit?
Yeah, so what we're
sustainability of it.
Yeah, so what we're excited about with manganese is the opportunity for a more sustainable redox center. And so you start from a different potential than cobalt. So if you use, manganese as a straight replacement, there is a difference in that initial voltage that you would realize for the system. But what we've been real happy to see is that with the right material design, including the crystallite size, the distribution within the electrode, you can actually get a manganese-based system that can have nice, sustained cycle life over time. So it's really about finding the right application. I don't think that we'll see a complete replacement of lithium cobalt technology with a system using only manganese as a redox center for a consumer portable electronic battery. I don't think manganese is necessary a one-to-one drop-in for that system. But if we're thinking about a long-duration battery that's giving us energy over time with different power requirements, I think manganese gives a great opportunity there. And if we're thinking about batteries that have intermediate power requirements and intermediate cycle life, I think there's also real opportunity for manganese there in these systems. Thanks for the question.
I have a question. One of the things that you hear about a lot is the idea that, as we move to a green energy grid where we're generating energy at times when we don't need it, storing it, and then distributing it when we do need it, that's going to require a more intelligent electrical grid. I wonder if you could comment on that, and is anybody in your group working on that problem?
Yeah, that's a great comment, and that's absolutely true. So if the grid today in most areas is really simple. You're generating energy, you're using it, or you're losing it. And that's the simplest way to design the system. If you want to store it and harness it and then provide it back, you need a smart grid. You need some level of feedback and control to make that happen. But what's really exciting is that I think this is an area where the utilities are motivated, and they've made a concerted investment to move in that direction. So at Brookhaven Lab, we actually hosted a joint strategic summit with Con Edison about 6 months ago. We had over 200 participants, including Con Edison and stakeholders, from the community, thinking about future grid and how to address some of these challenges. So I think that, as you said, it needs to be a smarter grid. It needs to be a little more complicated, but I think the time is now because we've got the resources to do it. The computational resources have advanced now that, the cost for sensing, the cost for the computer systems, to management is much lower. What we really need is just a little more investment in the science expertise and the folks that can do, the modeling work. And I think when groups like national labs and utilities and providers can work together, that can create a real opportunity, because there's work we can do to de-risk new systems, and there's work we can do, in partnership that's bigger than we can do as individual organizations. Thanks.
Hi, thanks so much for your talk. I'm Julie Byrne, and to follow up on Krista's question, another cobalt question. Some media reports seem to raise the alarm that cobalt mining is going to require ocean floor mining, even with the implication that there could be, dangers to sustainability and environmental degradation by the mining of cobalt that's needed for batteries. How do you, as a scientist working in this area, weigh the cost benefit of that? Obviously, turning to other materials is part of it, but thank you for addressing that.
Oh, thank you. Thank you for that question. Yes, when I read about, cobalt mining, it's really upsetting, both the current situation and the projection you talked about, going toward alternative cobalt resources. There's examples of, mining now that use, young people, children. There's really a unfortunate legacy, associated with cobalt and its access. So I think that the approach is really to continue to look at new systems which can function effectively and provide a good alternative solution. So the nickel, manganese, cobalt oxide I showed as an example, I showed a slide with sort of one example and one flavor, implying that it was one composition, but there's actually multiple compositions, multiple ratios of nickel, manganese, cobalt within that material that you can use. And so there's been a concerted effort to move towards systems that have lower and lower and lower cobalt amounts. And there's been advancements, by multiple groups in that area, through the U.S. Department of Energy's investment. So I think that if we think about a solution to removing cobalt, it may not happen immediately. I don't think there's a drop-in replacement now, but I think that there has been a lot of advance toward that goal, and I think there'll continue to be advance. But I think having both the, if we only use, cost as a driver, sometimes that's not the fastest way to get toward a sustainable solution. I think it's having a combination, recognizing both the need for an improvement for security of supply, for resiliency, for sustainability. I think it's important that there's a push or an impetus to go in that direction as well. Because if we look at solar, for example, and the success in to date in integration of solar, I think a lot of the motivations and incentives towards solar help make that happen. And then both the science can advance, the technology can advance, and then as they move in parallel, there can be more work. So I really think we'll be able ultimately to get away from cobalt, but I think that having investments, federal, state level, and then also having folks who are thinking about the social impact and being vocal about that is also really important.
Tremendous savings for local Long Islanders.
Yeah, I think geothermal is a great opportunity. When you think about geothermal as a system, part of the question is, how deep can you go and the details of how the well functions. But I think at the community level, I know, in my part of Suffolk County, systems that have heat pump-based systems and systems that are using storage, geological-based storage, have shown benefit to a lot of individuals. So I think there's a couple opportunities. One is looking at where are we putting our geothermal resource? Is it at the community level? Is it larger than a community for longer storage? I think that linking back to that smart grid comment is also useful as well for a resource like geothermal. What time scale do we want it to operate over? And then are we thinking about it as a microgrid, as a community grid, or as a distributed grid? So I think that having companies who are interested in this space, doing more partnership, more engagement, with universities and national labs could be helpful in the long term. And I think in the short term, just getting more awareness out about what these sustainable resources can do can be helpful. Because I think as more people try it or make a case that they want to try it, that will also motivate investment in these areas. Thanks.
All right, let's give our speaker one more round of applause for a really fascinating talk. And again, you'll be available outside to sign books if anyone's interested. And we will start up again at 2:40 with our next panel session on Hurricane Sandy. Thank you. Thank you for coming.